So the next speaker is Lixi, who I already presented with principal engineer at OneCloud.
Hello everyone, I'm Lixi from OneCloud, and I'd like to today to introduce some of our recent work. It is focused on the cache replacement policies, and it is targeted for the storage tiering of Lustre. So there is some background for the Lustre tiering. As we know, we have been talking about a lot of different storage types, for example, SSD, NVMe, NVRAM, and of course traditional tape and HDD a lot recently, and we see a lot more kinds of storage types coming, and they have different specifications. For example, the latency, capacity, bandwidth, and many other things. So we usually use hard disk for big capacity, but at the same time we use SSD or NVMe or the other high performance storage for cache or for the other purpose. And another thing we see frequently recently is we use different network to connect this storage to the system. I mean, Lustre storage or the other file systems. So we can see there is a very obvious change in Lustre. We will see multiple tiering levels in Lustre. So we do that for different reasons. For example, the major reason is that we want to get maximum performance with acceptable cost. So that means we want some kind of cache levels in different ways, and we want to provide better quality of service by doing that, and we want to utilize the storage locality, which is we might be able to find in some of the applications, and we want to move the data close to the compute, and it will accelerate our applications by doing that. And in general, we want to improve the entire efficiency of the storage system to make sure we provide better service to the applications or to the users. So that's the background. So because of this background, we are seeing a lot of more tiers in Lustre file system. We have a lot of technologies to do that. For example, we have discussed PCCA a lot recently, and Cambridge University mentioned Lustre on demand yesterday too. So we can use that for cache in some way, and also if we use SSD or NVMe for Doom, we can cache the data. Not cache, we can use that Doom to save the data and to accelerate the access of data. So there are other ways to do that. For example, we can use SSD to group OSD pool, and we use that pool to save the data which we think is important to be accelerated. And also we use HSM for the archive storage to save the code data. So basically we can build a system with a lot of tiers in Lustre. So, and another interesting topic that has been shown recently is we want to connect Lustre with other kind of storage, for example, the object storage, or we want to connect it with cloud. So it's a new thing that are coming. And here is an example of what we can see in a tiered Lustre file system. We can see HSM, which usually based on tape or other relatively slow storage, and we use archive and restore command to copy the data, to move the data between the Lustre OSTs with HSM storage. And even inside Lustre OSTs, we can separate different OSTs with different storage types into different pools, and we can do something special by doing that, we can save some data on the quick OSD pool to accelerate the IOs, and we can save other storage, other data into the slower storage, because the accessment of that storage of that data might not be so critical, and we are seeing that a lot of people are attaching NVMe storage onto the client, and there are multiple ways we can take advantage of it. We can build a last on-demand file system on the client side, and we need staging and stage out step to move the data between last on demand and the main last file system. And of course, if you are interested in PCC, you can also build a PCC storage based on the NVMe or NVRAM devices on the client side, and we use attach or detach commands to move the data between the OST and the PCC storage. So that's an example of how what we can do by using different technologies to build different tiers in last file system. So in these systems, we see a lot of new requirements that didn't exist before. For example, we need to decide what data where the data locates on. We need to decide whether the data locates on the quick storage or the slow storage. So in the recent years, we are trying to defining different technologies to do that. For example, PCC, we are implementing rule-based policies. For that purpose, you can define rules to determine whether the data should be created on PCC or not. Maybe the data is not suitable to cache in PCC, so you want to save the data directly into the normal OSTs. And for example, last on demand, we can create the files on the last on demand if the job is running, right? Because the job supposed to access that new files frequently. And also for Doom, we can inherit the stripe configuration from the parent. That means we can use that to configure what files to be saved in Doom. And also for SD pools, a recent work is data placement policy. So by using data placement policy, you can define rules to decide which OSD pool you want your data to be saved in. So there are a lot of existing mechanisms in Lustre in that area. And another area is data movement mechanism between tiers. And for example, PCC, you can it basically reuse the copy tool to restore or to flash the data from the PCC to the OST. And for the last on demand, we have more options. For example, we can use CP to do the data copy, or we can use parallel CP in the MPL5 utils. And for Doom or OSD pool, because it is some kind of internal feature of Lustre, we can use LFS migrate to do the migration of data. And another aspect of the requirement is how we can find the correct data to move between tiers. We need to find the hottest files to be saved in the quick tiers, and at the same time we need to find the coldest files to move out of the quick tiers, right? And in that process, we need to have some kind of cache replacement policy, and it is very important. So the reason why it is important is, well, cache replacement is always important, even in the memory management, right? Because we already know that, for example, Linux has been using mechanisms to decide what page to get rid of. But for the cache replacement between last tiers is even more important because it is really really expensive to replace data. And if we make wrong decisions, the performance will be hurt a lot. And this picture shows an example of what we will need to do to do a cache replacement. So there are a lot of steps. First step, we need to find the coded files to effect. And that will take a lot of time maybe. And step 2, we need to move the data out of the lower tier, and you need to do data copy and data removal. And there are other steps. You need to find the hottest files in the lower tier, and you need to move the hottest files into the upper tier. So as we can see, the cost could be huge. And well, there are several principles we need to keep in this process. We need to make sure that the upper tier is as full as possible, and you do not want to effect data unless it is really necessary, and you want to effect as little as possible because it is very important for the cache efficiency. So if we do some quantitative analysis of the replacement efficiency, we will get a simple formula. And in order to get this formula, we define some parameters. For example, we assume that we know the upper layer performance and the lower layer performance, and we know what data we are going to replace, and we know the excess amount of the effective code data, and we know that the excess amount of the fetched hot data. And of course, during this replacement process, we will have some overhead, and by defining those parameters, we get a formula, and well, the formula itself is not important, but we can get some meaningful results from the formula. The first conclusion is that we need to make sure that the performance difference between different tiers should be huge. I mean, for example, if you are building 2 tiers, one with HDD tier and another with different storage type, for example, NVMe or NVRAM, which are much quicker than the hard disk, most likely it wants to move data between these 2 tiers. But for example, if you only have 2 tiers with the same OST type, with the same storage type, and the only difference between them is whether the load is high or not between them. So in that case, it might not be worth to move the data between them because the performance difference is not huge and is not permanent, and it will change according to the load. So another conclusion we can get from this formula is that we need to make sure that our replacement is meaningful. We need to make sure that if we effect any data, the data should be very cold. And at the same time, if we move a data from the lower tier to the upper tier, we need to make sure that this data should be very hot. Otherwise, it will be meaningless and it will hurt your performance. And another conclusion is that we need to reduce overhead as much as possible, because as long as we reduce overhead, the performance or the efficiency will be improved immediately because of this. And we have multiple ways to do that, and one simple way or easy way is to use parallel data copy or removal commands to do the data movement. And if we made a general conclusion, we can say that data replacement is really important, and we need to choose the correct data to move between tiers, otherwise it will hurt our performance. One thing that we find in the data replacement is we think that finding the coded files to effect is very hard. If we think about finding the hottest file, it is relatively easy because we can maintain a heap of file heaps in the memory, and you can always get the hottest files in the top of the heap. And it is simple to implement, and it is very efficient. But in order to find the coded files, the coding is a little bit difficult because first you need to manage millions or billions of files because Lustre is very scalable and you could have billions of files. And you cannot do that by keeping some kind of data structure in memory. For example, LRU or heap, because the memory size is not large enough. And another cause of the difficulty is that we are not able to predict the access time precisely. And that means you cannot define a simple rule to say, oh, I want to find out, for example, the files that are not accessed for a day, and I want to evict those files. And that might not be useful because these files might be very hot files, and you might, and in another condition, you might not be able to find any of these files because all of the files are being accessed in the recent day. That's another difficulty. There are other reasons why it is difficult. For example, there might be some files that has never been accessed. So that means you need to work through all the file system, the entire file system, to find the very coldest files. And as we know, scanning the whole file system is expensive and it is relatively slow, even you use policy engine. But finding the coldest file is, how to say, we need to make sure it is very quick, and even policy engine can find the files quickly. It is not quick enough because it depends on how large the file system is. So that means we need to implement in a different way and to make sure that the cost would be constant. So that's the reason why we recently implement a system called LCMP. So it means Lustre Cache Management Policy. So it is public, so you can check the code and the implementation. So the major idea of it is we maintain on-disk structure of file list, and the file list include multiple levels, and you move the files between different levels, and the lowest level will contain the files that has not been accessed for a long time, and the data structure on the disk will be synchronized with Lustre file system from time to time using the changelog, and the time is divided into epochs, and at the end of epochs, you move the files between different levels. In that design, you can always find the coded files in the lowest level with constant time, no matter how big the file system is. And that's the idea. So as we can see, there are multiple levels, and in each level there are a lot of files, and you need to move the files between different levels. And if there is any file being accessed, the file will be put onto the top level, and it will be downgraded to the other levels. And you can always get the coded file in the bottom. So if we go into a little bit details of LCMP, we will know that we use directory tree to save the data structure, and we maintain 2 directories for this data structure. We maintain a FID directory that will enable us to map from FIDs to unknowns quickly. And at the same time, we maintain LRU directory tree. So LRU directory tree maintains the levels that we mentioned before, and it will create hard links to the FID directory tree. So the number of the hard links will show us whether the files has been accessed more recently. So that means we need to maintain the hard links properly, and we need to clean up hard links from time to time. So this is the general idea. So when we have changelog, we update the levels, and the levels will downgrade from time to time to the next level. And another thing we need to do is to do an entire scan of the tier to for the original injection of the information. And this picture shows some details of the directory tree. For example, in the global directory of LCMP, we have two subdirectories. One is LRU and the other is FID. So in the LRU directory, you have different levels from level 0 to level n, and it will downgrade from one level to another. And in the level 0, you will have the files that has been accessed recently, and those information can be got from the changelog records. And as the downgrade keep on going, and you will always find the coded files in the in the bottom level, right? And there's another directory, FID. You can always use the directory FID to find the files that you are looking for by giving an FID. And the relationship between these two levels. So the system keeps hard links between these two directories, and you know whether a file has been accessed recently by checking whether there are more hard links than you expected. So if we analyze our LCMP design a little bit, we know that LCMP should have good scalability because we know that the maximum inode requirement is the same with Lustre file system, and we don't need a lot of space for LCMP, and so that means a device with the same size or even smaller than MDT, we should be able to maintain the data structure of LCMP already, and also we are able to support Lustre file system with billions of files. And even you are using DNE, you can easily support that by creating multiple LCMP directory. And also, another very important thing is, of course, we need to make sure that we can find the coded files in the O1 time. And it's very important because that's our purpose. And even by accomplish that purpose, we do not need to use very good storage for LCMP because LCMP is not I/O intensive. And another advantage of LCMP is we don't need to configure a lot of complex parameters for LCMP because we only have 2 parameters to tune, and usually the default values for these 2 parameters should be enough for most of the use cases. And another advantage is we can use the same mechanism for a lot of different tiers. We can use that for PCC, we can use that for Lustre on Demand, Doom, OST pools with different storage types, and also HSM. So we can use that for a lot of kinds of tiers, and also we do not need to patch Lustre a lot, and you can use that for any Lustre version as long as the changelog is supported. And I think most of the Lustre file system that are in production has support for changelog. But of course, we need to optimize LCMP a lot in the future. Some of these things have not been finished yet. For example, we need to scan the whole file system for original injection. And also, we can use police engine for that purpose, right? But also, we can simply walk through all the directory trees. So another optimization that we need to do is to filter the changelog record. We need to do that because we want to avoid evicting some data because of some attributes or IDs, for example, UID, GID, or maybe you have a VIP who you don't want to evict from the higher tier to the lower tier, and we need file filtering mechanism for that. And for different tiers, we need to optimize and customize LCMP a little bit for them. because, for example, the time granularity is different for different tiers. For example, PCC, you want to make sure that the time is small, but for HSM, you might do not care what happens in the recent hours. But there are other optimization we need to do. For example, for PCC, we do not have changelog for PCC. So for PCC storage, because they use EST4 or other kind of local file systems, but we can implement some mechanisms to for the modification. For example, we can use Linux and Notify to do that. And there are a lot other optimizations and customizations for different tiers, of course. So as a conclusion, we realized that there will be multiple tier levels in many Lustre file systems, and it is becoming more and more common. And because of this, we realized that cache replacement policy between different tiers is very important. And one of the major difficulty here is how to find the coded files to effect, because it is important but not easy, not as easy as other mechanisms we need. So that's the reason why we designed and implement a tool to do that. We call that LCMP, and we think that it will be able to list the coded files in the O1 time. And that's all. So any questions?
Questions?
Okay, so I'm not sure how different that is from a very specific policy engine, but a few questions. You are having hard links in directories based on times with exponentials, so the older time slice will be very big. We're talking like million of hundreds. How are you dealing with that?
Sorry, what's that?
You're saying that listing in O of 1 for the coldest files, but it's going to be a very huge directory. It's going to be slow.
So it is a huge directory, but you do not need to list all of the contents in the directory. You need, so most of the time we need to only find some files to effect from the cache levels to make enough space for the data you want to move from to the upper tier. So that means you just need to find some files to effect.
But it's still going to be slow to manipulate the directory, even if you don't need to read there's a world directory. The Lustre cache will read everything. Anyway, next question I had was, you're only considering changelogs, but you don't get any changelog for access time. So if a file is only read, you will never see that it's being used.
No, so you are considering read. So you're considering maybe a file has been read, but the system is not able to know it has been read recently.
Yeah.
I think even you, for example, I think I know that the A time will not be updated as every time when you read the data, right? Because you. Because the A time will only update it when the files has been closed. So there is obviously some limitations for that, and changelog is not be able to cache all the IOs.
No, but you won't get any changelog for A time updates, as far as I know.
Sorry?
You're not going to get a close event if the file was opened in read-only mode.
Maybe you think that there are some events, but there are 0 events about A time in the changelog records. It's only
right. So I think we need to. So currently we haven't looked into the changelog records right now, but in the future we might need to change the changelog a little bit to input input some information into the changelog records and to make sure that those records are meaningful and useful for the LCMP data management. And another idea from Andreas is to put into the system into MDT, so we do not need changelog to input the information that we need for the maintaining the data structure.
Okay, thanks.
Okay.
The LCMP namespace, it resides in the Lustre namespace like any other object, or is it a kind of shadow namespace like Lustre?
Yeah, we need some kind of shadow namespace. We need a directory to save the data. So that's the reason why we need another storage outside of MDT to maintain the data structure. So yeah, that's the current implementation.
Do you have other questions?
Maybe I have one if we have time. Aren't you afraid that with the policies that you're suggesting, you're forcing your use cases on users and administrators? I mean, for example, you say that we always want to have the hottest level of cache full so that reading is fast, but maybe someone wants to have the hottest level of cache free so that they can write very rapidly without evicting anything. Is there some way that you're planning to make this configurable so that administrator can choose which behavior they want?
So how to say, the current implementation of LCMP is trying to only solve this problem of finding the codist files. But at the same time, I'm trying to think of whether there is anything else that LCMP is able to solve by using the similar idea to maintain a data structure outside of MDT or inside MDT and to make sure that we can find whatever we want to find quickly.
Okay, thank you.
Okay, thank you.
Thank you.